Today we're looking at the equilibrium concentration. So as a follow-up to the last one we did, we looked at how we can calculate the equilibrium constant. Well, first solved equilibrium expression problems. That was back here. So we saw that the equilibrium expression constant is written with this equation. And so we can write the expression. We practiced that. We saw that when we have heterogeneous equilibrium, we include pure solids and liquids as one. And then we saw that we can calculate the constant. Now we're just going to take one more step, and we're going to solve for other unknowns other than, say, the constant. This problem, we're given the constant. Let's look at the problem. We have, oops, wrong one. So we have this equation. We're given the constant. What is the equilibrium concentration of carbon monoxide given the concentration of everything else? Some applications of this, for instance, we'll see similar applications from bases, especially looking at buffer solutions, which are very important in a lot of health fields as well as in biochemistry. So let's see how we can approach this problem. Now the of course is just simply writing the equilibrium expression. So if Kc is the concentration of the products, CO times H2O, all divided by the concentration of the reactants, so that would be CO2 times H2. Now, the difference here is that our unknown is CO. So this is what we're trying to solve for. So to solve for that, we're going to need to isolate the CO. We could put the numbers and then solve, but I'm going to show you by first solving for the variables. So we have to by both sides by CO2 times H2 and so that's going to cross out here. Get this expression then. So CO2 times H2 concentration times Kc is CO concentration times H2O. And divide both sides by H2O. And on the left we have divided by. Need to plug in the numbers and calculate 0.25. We don't include the units, the concentration numbers. 0.80. Constant 0. Divide H2O concentration 0.50. All right, so we do, and that comes out to 0.44. And now we can replace the unit again. The unit is molarity, since the brackets mean concentration and molarity. Let's try another problem. So this next problem, we have this equation. The constant is, if we have the concentration of NO and the concentration of Br, what is NOB concentration? The first step is writing the equilibrium expression. So given that equation, the equilibrium expression for this, let's pull this down. So again, we're doing this problem. So the equilibrium expression for that, this, Kc equals NO, brackets squared because of the 2 coefficient, times 2, all the and Br squared. All right, and so we're going to be solving for NOBr. We need to isolate that. I'm going to multiply both by NOBr, divide both sides by Kc. You end up with expression. NOBr squared is NO squared times R, concentration divided by Kc. Now I need to take the square root to get NOBr solved, to solve for NOBr. So NOBr concentration is the square root of NO squared times BR over KC. Now if we plug in those numbers for this equation, NOBR then is, plug in those numbers, so we have 2 for NO, and BR is 1, and KC is also 2. So we're going to have 2 squared times 1 all over 2 square root. So then the NOBR concentration, 2 times 2 squared is 4, divided by 2 is 2, is the square root of 2. Now in science, we don't leave that as the square root of 2. We find what the square root of 2 is. So 2 square root, and out 2, 1.4, 1.4, I'll round it to 2 places. So NOBR concentration is 1.4 unit molarity. Do we need to put plus or minus since we took the square root? Well, the negative is automatically thrown out. We don't include the negative, no negative concentration values are possible. So concentration is a positive value, so we can just throw out the negative solution to the root.